So today we'll be doing questions from week 7, and if time permits, we'll take the doubts towards the end from this week. Have you guys tried questions from this week? Am I audible? Okay, so this is the first question. Give this question a try and then we'll do it here. And actually, let's do it here only because it's a very simple question. So we'll do this one here and you guys can try the other ones. So this question is about the limit of this sequence. So to find the limit where you see that the power here and here is the same, that is in the numerator and the denominator, if you see the power is same, you can just divide by the highest power. So that means if you have n cube, we did a similar question in the last class as well. So in this particular case, if instead you had n square plus 1 by 2 n square plus 1, then you could just divide this entire numerator and denominator by n square. But for this one, you have only n. So this is, you can write this as 1 plus 1 by n. So we are dividing the numerator by n and then the denominator by n. So we'll have this. And then we can take the limit as n tends to infinity. So this will be 1 plus 0, and in the denominator, you'll have 2 plus 0. So it will be half. Okay. So this is the
Ma'am, in
next
the previous
question.
question, did we really have n plus 1? The question had only n by 2n plus 1, right?
Okay. If it's the same thing, this is anyway just going to 0. Yeah, we don't have n plus 1 here. We'll get the same limit anyway. It will be troublesome if I add a higher power here. That will be a problem, but otherwise it's the same thing. And yeah, we don't have one here. So it should be this way. Okay. Can we move to the next one?
Yes, ma'am.
Okay. So this is the next question. Give this one a try. Anyone done? Are you guys trying the questions? Or should we do it here? Okay. So for this one, first you have to figure out if n tends to infinity, if your n tends to infinity, so log n tends to infinity as well, right? Your graph for log n is basically this. But if we just consider natural numbers here, like this one, 2, 3, 4, 5. So if you will consider this, this is a1, this is a2, this is a3. Then as an, as you move, not this is 1, 2, 3, sorry. This is this is 1, 2, 3, 4, 5, and this will be This thing, this here will be 2 comma log 2. Then here you will have 3 comma log 3. Then here you will have 4 comma log 3. So you see, and this log n is basically the height of this function only, right? So as your n tends to infinity, your height's also going to infinity. So this will tend to infinity because your function simply goes to infinity when x moves to infinity. That's why this goes to infinity. Then 1 plus log n will also move to infinity. And this means your 1 plus log n raised to the power 1.1 is also going to infinity. So this is 1 by 1 plus log n 1.1. This will go to 0. If this entire, if you have anything that's going to, if you have an going to infinity, then 1 by an goes to 0. So this thing will go to 0. And this would mean that 2 minus this thing, 1 by 1 plus log n to the power 1.1 will go to 0 as n tends to infinity. Is this okay?
Yes, ma'am.
Okay. So this is the next question. Give this one a try. This is a direct identity though that we've discussed in last class.
Ma'am, excuse me, ma'am. Ma'am, the previous problem, 1 minute, ma'am. 2 minus that 2, why the answer can't be 2?
That is true. That's just a mistake. I messed this in hurry. We have to have 2 here, right? This entire thing
Okay.
is going to 0 and this is 2. Okay.
Okay, ma'am. Okay.
Is anyone done with this question? Okay, so in the last class, we had some limits, some important limits that were supposed to be learned. So one important limit was x to the power n by n factorial, or x, let's take k here, x to the power k by k factorial when k varies from 0 to n. The limit of this thing, this is a sequence, and this sequence goes to e to the power x, right? So what is, and this thing is exactly this, right? You will have 1, then you will have 1 plus x, because it's starting from 0, so you will have x to the power 0 by 0 factorial, that's 1. Then you will have x to the power 1, so you will have this thing. Then in the next one, you will have 1 plus x square by 2 factorial. In the next one, you will have 1 plus x square by 2 factorial and x cubed by 3 factorial. and it keeps going on. So this is this, if this is the sequence, then the limit of this sequence is this tends to e to the power x, right? So this is the same sequence that you have, right? If this is an, if this is your sequence, this sequence, what is the nth term of this sequence? It is 1 plus x. This is the first one, this is the second one. Okay, so they have taken the nth term to be x to the power n by n factorial. That means your second term should be this one. First term should be this one then. That doesn't matter. Okay, so you can take it from here. Even if you remove this thing, you will have this as first term, this as second term. Also, if you have a sequence A1, A2, A3, and it keeps going on, and let's say this converges to A, even if I'll remove some finite number of terms from the beginning, let's say I remove these ones, and now my sequence starts from A4, and then A5, A6, and so on, so on. This sequence still converges to A, right? Removing finitely many terms from the beginning or from somewhere does not change where your sequence is converging. The point of convergence does not change, right? So that's why even if I remove the starting one, it's not going to change the point where this sequence is converging. So this is A1, A2, this is A3, and an then is 1 plus x squared by 2 factorial plus so on till x to the power n by n factorial. So this is your an, which is given here. You have to find the limit. That means you have to find the limit of this sequence, and this goes to e to the power x, as we discussed in the last class. So this should be the correct option. Can we move to the next one if this one's clear? This is just identity. We did this identity in the last class, which you have to remember. Not identity, this is an important, under the important limits, we discussed this limit, right? So you just need to remember this. If instead you see something like 1 plus 2 plus 4 by 2 factorial plus 8 by 3 factorial and so on. And then you're asked the limit of this one, then it's the same as instead of x, in place of x, we've substituted 2. And that's when we get this thing. So this should be converging to e square. Can we move to the next question if this one is clear?
Yes, ma'am.
Okay. So this is the next question. Try this one.
Minus 4.
Okay. So for this one, there are like multiple ways to do this one. First is the one that we used in our first question, which will be this. You divide this entire numerator, the numerator and denominator, both by x square. So in the numerator, you will have 1 minus 4 by x square, and here you will have 1 minus 5 by x plus 6 by x square. Okay, but this is not going to, okay. So you cannot use this one because your x, this time your x is not going to 0, it's going to 2. So instead, what you will have to do is you will have to, then we're only left with one way, which is factorization. So you factorize the numerator and denominator and try to cancel. Let's first substitute 2 here, because we don't yet know that it's 0 by 0 or infinity. We only have a problem when in fractions you get 0 by 0 form. The problems that we have are 0 by 0 form or infinity by infinity form or 0 into infinity form, which is identical to these two forms only. And then 0 to the power infinity. These kind of forms is what we have a problem with, right? So this, let's look at this one. If you'll put 2 here, you'll have 4 minus 4. So in the numerator, you'll have 0. If I'll put 2 here in the denominator, you'll have 2 square, which is 4, minus 10 plus 6. So this is again 0. That means you have a 0 by 0 form. So to deal with this 0 by 0 form, one way is to factorize, because we know if you're getting 0, 0 here and it's a polynomial too. So what's happening is this, that means you have a factor here. That means when I substitute 2 here, this is a polynomial, and when I substitute 2 in this polynomial, I get 0. That means 2 is a 0 of this polynomial. That means x minus 2 is a factor of this polynomial, and here is the same things happening here, right? If I call this polynomial qx, the numerator 1, the denominator 1, then q2 is 0. That means x minus 2 divides both this one and this one. And that is what is creating the problem here, right? If I'll remove that factor from both numerator and denominator, then the problem will be resolved. So that's why we factorize the numerator and denominator to remove the common factor that's making the numerator 0 and the denominator 0. So this will be x minus 2x plus 2. And in the denominator, you will have x minus 2 and x minus 3. So this you can write as this thing. And then we cancel, because this, if you put 2 here, we don't have a problem here. We'll get 4. But the problem starts here. When you put 2 here, you get a 0 here. This factor is the one that's creating trouble. Similarly, this factor here is creating trouble. So these two, if we'll cancel, we'll be left with x plus 2 by x minus 3. And we can find the limit of these. So if I take x tending to 2, I can take the same thing here, x tending to 2, and this will be, now I can substitute 2 here, right? Because the problematic factors are gone. So this will be, if I'll put 2 here, I'll get 4. If I'll put 2 here, I'll get minus 1. So this will be minus 4. One thing that we've not discussed in these forms is, maybe we'll have a question later, we can discuss it there, or I'll discuss it here. If you see, these are called indeterminate forms. And for these kind of forms, you can use L'Hopital's rule. So L'Hopital's rule is basically a rule when you see 0 by 0 form or infinity by infinity form. In these kind of forms, what you can do is, or if you have 0 into infinity form, let's say if I have x square and 1 by x plus 1. So if you look at this, if x goes to 0, this goes to, or let's take x, let's take sine x here. If I'll take this thing, x square by sine x, or let's take, if I'll take x square by cosecant x, let's say this. Then when x tends to 0, this thing tends to 0. And when x tends to 0, this thing tends to infinity, right? Because this is 1 by sine x, and sine x, when x tends to 0, this tends to 0. So this entire thing will tend to infinity, right? But the problem, or you can take cosecant square to avoid negative positive if there's anything wrong there. So we're, for the simplest side, we're taking this thing. So this thing is going to 0, this side, this is going to infinity. So you can write this is 0 into infinity form. But this can be rewritten as 0 by 0 form or infinity by infinity form. I can rewrite this form as these forms. And how can I do this? I can simply write this as, in this one, I can simply write it as x square by sine square x. Or if, let's say you don't know that you have a function, if you have something here which is tending to infinity, but you don't know what's the reciprocal of that function. So you can simply write this as x square 1 by cosecant square x. We know that this thing is sine square x. That's fine. But if you don't know it, you can still write this as this, right? Now this is going to 0, and this thing is again going to 0. Right? So you have this thing 0 into infinity form converted into 0 by 0 form. Right? So this L'Hopital rule works for this one as well. For these kind of forms, when you see something like this, what you can do is, let's say you have fx by gx, and as x tends to infinity, as x tends to a, this tends to 0, and this also tends to 0. That means you have 0 by 0 form, right? So instead of putting the a directly here, what you can do is you can take the derivative of numerator. So limit, if this is true, if this is 0 by 0 form or 0 infinity by infinity form, 0 by 0. So if this is 0 by 0 form or infinity by infinity form, then limit x tending to a, fx gx is the same as limit x tending to a, f dash x g dash x. These two are same. And if this also gives you 0 by 0 form, or if this again gives you an indeterminate form, then you can take it further and do limit of f double dash x by g double dash, this limit. Then you can take limit this thing. So we can keep going on like this. So you can keep taking the derivatives of numerator and denominator as long as until you get rid of 0 by 0 and infinity by infinity, until you get rid of indeterminate forms. So we do this to get rid of indeterminate forms. For example, let's take the same thing, the same example here. Example, let's take x square by sine square x. Now, if I take limit x tending to 0, then this will give me 0 by 0 form. To resolve this, I'll take the derivative. So I'll say limit x tending to 0, x square by sine square x is the same as limit x tending to 0 and the derivative of numerator, which is 2x, the derivative of denominator, which is 2 sine x, and then the derivative of sine x, which is cos x. You will see the derivatives in week 8, I guess. There's a topic for derivatives there. You'll have to learn the derivatives of basic functions there. And then you can apply L'Hopital's rule. So when x tends to 0, now where does this go? When x tends to 0, this goes to 0. And when x tends to 0, this denominator also goes to 0, right? That means you have 0 by 0 form again. This is 0 by 0 form again. So as long as there's 0 by 0 form or indeterminate form, you can continue to take the derivatives to get rid of it. Then you will do x tending to 0 and then take the derivative of this one. You will have 2. Take the derivative of the denominator. You will have 2 here. Derivative of sine x is cos x as it is. And derivative of cos x is minus sine x as it is. So you will have minus sine square x. So this is what you're going to have. Now, if I'll take x, this is just cos 2x, if you remember. We discussed this in the last class. In some properties, we discussed that cos square x minus sine square x is cos 2x. So this is cos 2x. And as x tends to 0, cos 0 is 1, right? So this is 1. That means your limit should be 1. Note that you can only use this rule where you take the the derivative of numerator and denominator and then find the limit. You can only use this when you have an indeterminate form. Otherwise, you can't do that. So this is L'Hopital's rule. You can apply this too. Now, in the question that we had here, this one, no? This one, we had 0 by 0 form. So instead of cancelling these things, what you could have done is alternatively, because you're getting a 0 by 0 form, if I'll put x is equals to 2 here, I'll get 0 by 0 form. So I can use L'Hopital's rule, which says take the derivative of the numerator. For the numerator, the derivative is 2x minus 4. Don't worry about how to find the derivatives because you will study that in next week, week 8. For now, you just need to know how you can use L'Hopital's rule to find the limits. So this will be 2x minus 4, and this one will be 2x minus 5. And this you can take x tending to 2. What is this? So here you will get, wait, this is 2x. Okay, you won't have a 4 here, right? If you take the derivative of x squared minus 4, you will just have 2x. This will be 0. No, this will be 4. So in the numerator, if I'll take limit x tending to 0, you will have 4 here. And here you will have minus 1, which is what we got here, right? Using this one, minus 4. So we get the same using L'Hopital's rule. Can we move to the next question if this one is clear? Is this question and what we've discussed in L'Hopital's rule clear to you people? Can we move to the
Yes,
next
ma'am.
question? Okay.
Yes.
So this is the next question. Just 1 second. Give this question a try then. Or maybe we have not discussed how to do such questions, so I'll do it here. So in such type of questions, one is if someone knows how to find the derivatives, you can use the derivatives because this is going to be, it's not, if I'll put first, you have to put 1 here and see what you get. So if I'll put x equals to 1 here, I'll get 2 minus 2, this will be 0. And if I'll put 1 here, I'll get 0. So I'm getting 0 by 0 form. So either you can use your L'Hopital rule if you wish to, or you can try to rationalize this. So this will be, you can multiply and divide by x plus 3 plus 2, x plus 3 plus 2. So if you have something like this in square roots, what you can simply do is, if you have square root of x minus a, and then something here in the denominator, and you're getting 0 by 0 form. So what you can do is you can take square root of x plus a here and square root of x plus a here. Divide and multiply by a square root of x plus a. That's what we've done here. So now try this. Okay, let's do this one here. So this is going to give me, if I'll multiply this with this, I'll have x. So here you can use the formula. This is a minus b. This is a minus b form, and this is a plus b form, right? If you will take a to be square root of x plus 3 and b to be 2, then this is of the form a minus b, and this one is of the form a plus b. And this a minus b multiplied with a plus b gives you a square minus b square. So that means this should give you the square of x plus square root of x plus 3 minus square of 2 divided by x minus 1 square root of x plus 3 plus 2. So this gives us x plus 3 minus 4, which is just x minus 1. And here you will have x minus 1 and square root of x plus 3 plus 2. So these two gets cancelled. And finally, you have this expression. This expression is the same as this one, and this is the same as this one. And this is just 1 by square root of x plus 3 plus 2. So when x tends to, what is given? When x tends to 1, what is this thing? This is, now you can simply put x equals to 1 here. You will have 2 plus 2. This will be 1 by 4. Is this okay?
Yeah.
Okay. So now try this one. This is a similar one to what we did in the last one.
Multiplied by 4 plus root 15x plus 1 by 4 minus 15x plus 1.
Okay, solve this and let me know what answer are you getting. So for this one, someone suggested, which is right also, but it's partially correct. You'll have to do more than that. If you do this thing, 4 minus, we already know that if I'll put 1 here, I'll have 15 plus 1, 16, and the square root is 4. So this will be 0, and this will be 0, 2. So this is 0 by 0 form. First thing is to notice that it's an indeterminate form. And second step is you rationalize the numerator, but if you do that, you'll have 15 x plus 1, and then you'll do 4 plus square root of 15 x plus 1. And then you will do the same in the denominator, right? So this will be 4 plus square root of 15 x plus 1. Now if I'll solve this one,
4 minus, madam, in the denominator.
why 4 minus? You
No,
can't.
4 plus,
Okay.
4 plus, yes, same.
Okay. So this thing will give you 16 minus 15x minus 1, right, in the numerator. Using the same formula, a minus b, a plus b is equals to a square minus b square. Then here you will have 2 minus 3x plus 1 and 4 plus square root of 15x plus 1. Now if I'll take the limit here, x tending to 1, right? So if I'll take x tending to 1 here, this will be 16 minus 15 minus 1, which is 0. And if I'll take 1 here, remember this was the problematic factor which was giving me 0 at x tending to 1. This factor was giving me 0, right? And it's still here. This factor is still here. That means it will give you 0 again. This is 0 by 0 form again. So further, you will need to rationalize this part too. This one. This has not been rationalized yet, right? So for this one, you will multiply with 2 plus square root of 3x plus 1. And you will do 2 plus square root of 3x plus 1. So this will give you 16 minus 15x minus 1. This is 2 plus 3x plus 1. And I can write this as, okay, this is just 15, right? 15. Okay. And here you will have, so I'm keeping this one as same, 4 minus square root of 15x plus 1. And this is the one that's supposed to rationalize this one. So with this one, these two, I'll have 4 minus square of this, right? So this is 3x plus 1. So this will give me 3x minus 1, which is just this thing, right? And then this thing is, this is just 15 times 1 minus x. And this is, just give me a minute. Yeah. So here, this is the same as 50. So we have a factor 1 minus x here, and we have a factor 1 minus x here. So what happens is when you have such type of questions and you're getting 0 by 0 form, even if your x minus 1 factor is not very visible, x minus 1 is not a factor of this one, right? If you will divide x minus 1 is not actually a factor of this one, but if you will multiply it with something, there's some part of it here. That's why we're trying to get the factors of x minus 1, because if x tending to 1 is giving you 0 by 0 form, that means your x minus 1 and x minus 1 from here and here should get cancelled. But you can't do it by using factorization, because the factorization part is not applicable to such factors, such this is not even a polynomial. To these expressions, you can't factorize 4 minus square root of 15x plus 1. That's why instead we rationalize it. So here you will have, now here you have a common factor. So if you're getting 0, the point is if you're getting 0 by 0 form, then it's pretty clear that you're going to get x minus 1 and x minus 1 from both cancel. That is when this problem is going to get resolved. And the L'Hopital rule say it solves the same problem, but in a different manner. When you do f dash x by g dash x, that factor gets removed. So you will have this is 5 1 minus x, and this is 15 3 1 minus x. So this one will get cancelled from this one. So you will be left with 15 times 2 plus square root of 3x plus 1. And here you will be left with 3 times square root of 4 minus square root of 15x plus 1. So when your x tends to 1, Here you will have 15. This will be 2. So here you will have 4. And this will be 3. And this will be, do we have a negative here or a plus here? We should have a plus here, right? Yeah. So we have a plus here. So this will give us 4 plus, and here also you'll get 4. So this will be 5/2. This is going to be the answer. And alternatively, but it's not going to be very easy. You can apply L'Hopital's rule too. If you want to, you can apply L'Hopital's rule to numerator. Take the derivative of this, take the derivative of this. But because you've not done derivatives, you'll do them in week 8. Then you can use that form too, the L'Hopital's form. So the last question is clear, right? This one. We move to the next one if this one is fine. Try this question. Before you solve this, although it should be clear from the increasing functions one, your increasing sequences, we say that an is an increasing sequence if an is less than an plus 1 for all n belonging to natural numbers. That means every term, if this is a1, this is a2, this is a3, this simply means that a2 is greater than a1, a3 is greater than a2, and a4 will be greater than a3. So each time it keeps increasing, right? Or you can use equal to 2. That's your monotonically increasing sequence. And the decreasing one is where this is greater than equals to. The sign will change for the decreasing one. Now try this one. Is anyone done with these options?
Option D, ma'am.
Okay, option B, you have to find monotonically increasing functions. That means each term should be the next term. If this you have 2 terms, 2 consecutive terms, this next term should be either equal to this or it should be greater than this. So you have to find which one of these is a monotonically increasing sequence. Okay, let's do
Madam,
this one.
the first term itself is a sequence. It just says that n by n plus 1.
First, don't know this. In the first option, the sequence is this. First is this sequence. That means this is the nth term. If this is your sequence, this is the nth term of your sequence. That means A1 is 1 by 2. A2 is 2 by 3.
2 by 3.
A3 is, so this is a sequence, and they're asking whether this is an increasing sequence or not.
So this is
That's
an
the
increasing
question.
sequence in that sense.
Okay, how do you show that it's an increasing sequence? This is the definition for an increasing sequence. You have to use this. Okay,
What
for
is
the
the
first option, yeah,
what is the definition of the increasing sequence?
increasing sequence is simply when you have A1, A2, A3. That means if you have AN here and AN plus 1 here, this term should be greater than this term, right? Each time it should keep increasing. A2 should be greater than A1, A3 should be greater than A2, A4 should be, I'm saying greater, but it can be greater than equal to. So I want A2 to be greater than equals to this, A3 to be greater than equals to this, A4 to be greater than equals to this. If this is followed throughout your sequence, this pattern is followed throughout your sequence, then it's an increasing sequence, monotonically increasing sequence, right? So in simple, either instead of writing this entire thing, can I just not write that AN should be less than equals to AN plus 1? This will cover everything, that A1 is less than equals to A2.
Less or is equal.
A2, yeah, A2 is less than equals to A3, A3 is less than equals to A4, and so on, right? It should keep going on like this.
So if this sequence is n by 1 plus n, it is an increasing sequence. But first you get 2, then you get 2 by 3, then you get 1.
But you don't, sometimes what happens is, this is just a hunch, right? That it looks increasing. Sometimes
That's
your sequence are increasing till here, let's say increasing till 10, and then it starts decreasing. That can happen, right? You can't
correct.
check for each and every term. So you
Correct.
should check it in a general manner. General manner means what is AN? AN is n by n plus 1, right? This is AN. What is AN plus 1? AN plus 1 is n plus 1 by n plus 1 plus 1, right? So n plus 2. And what do I need to show? That if this is an increasing sequence, then this term, this should be greater than equals to this. So I have to prove that n plus 1 should be less than equals to n plus 1 by n plus 2. That means I have to prove, equivalently, I can prove that n by n plus 1 minus n plus 1 by n plus 2 is less than equals to 0, right? Same thing, I've taken it on this side. If I have to show that AN is increasing, this means I have to show that AN is less than equals to AN plus 1. This is the same as showing n by n plus 1 is less than equals to n plus 1 by n plus 2, which is the same as showing this thing. That this entire term is less than equals to 0. So let's see. This is n plus 2 minus n plus 1 squared by n plus 1 n plus 2. Let's have a look at this one, the denominator. N plus 1 is greater than 0, right? This is greater than 0. This is positive. N is a natural number. And when you write these things, an, your n has to be greater than equals to 1, right? You start your sequence with a1, a2. So this is positive. Even if you'll take n to be 0, it's still positive. This will always be positive for all natural numbers. This is also always positive for all natural numbers. Now let's come to the numerator. That means numerator will decide everything, whether this entire thing is greater than 0 or less than 0, or it can be anything, right? So this is, your numerator is n square plus 2n minus n square minus 2n minus 1, right? So these two get cancelled and you will just have minus 1. That means the sign of your numerator is negative. Your numerator is negative. This is positive, positive. That means this entire expression is negative, right? And this entire, what is this? This entire expression is simply an minus an plus 1, right? We simplified an. This is an. This is an plus 1, right? So that means this thing is less than equals to 0, which means an is less than equals to an plus 1. That means our sequence is increasing. And because we have proved in general, we have not proved that A2 is less than equals to A3 and something like that. We have not proved for a particular term. We have proved for every term there. That means an is an increasing sequence, right? Is this okay? Is this clear to all? Or do you guys want me to repeat this?
Right, it is clear.
Okay. So that means your first option is correct. This is an increasing sequence. And let's come to the second one. It is -1. Let's first have a look at what your sequence is. -1.
Madam,
One.
in the first, you take the minus of an minus plus 1 minus n, or an minus n plus 1.
It's the same thing. No, see, if you want to prove that an is less than equals to an plus 1, this is what you'll have to prove. If you have to show an is increasing, this happens if and only if an is less than equals to an plus 1 for all n belonging to natural numbers, right? And this happens if and only if, this is the definition for increasing sequence. This happens if and only if an minus an plus 1. If I'll take this one on the other side, this one, I'll get this, right? For all n. And this is the same as saying, or now instead if I take this on this side, I'll get an plus 1 minus an greater than equals to 0, right? For all n. So either you show this thing or you show this thing. It's the same thing, right?
Okay, got it.
We have used this one. You can use this. If you will find this expression, you will get it positive. You will see that this expression is positive. In the
Got
same manner that we've seen that this is negative. Okay. So coming to the second sequence that we have, it's this. Now our definition says, just 1 second. Okay. So our definition says here, and what is the definition of decreasing? So for a decreasing sequence is this. I'll also write the definition of decreasing sequence. Bn. Bn is a decreasing sequence if Bn is greater than Bn plus 1. So this is the n plus 1th term. This is the nth term. So if your n plus 1th term is less than nth term, that means if this is nth term and this is n plus 1th term, the next term, right? Then this n plus 1th term should be less than the last term. Similarly, this term should be less than the last term. This term should be less than this one. That's your decreasing sequence. That means each time either your terms decrease, if these are your terms, then they are going to decrease this, then this will be lesser, this will be lesser, this will be lesser, or they'll be equal. That's it. So it's decreasing, Bn is decreasing if Bn is greater than equals to Bn plus 1 for all n belonging to natural numbers. So we have seen what an increasing and decrease, and when it's neither increasing nor decreasing, like this one. If you see this, A1 is less than A2, right? And then A2 is greater than A3. What's happening? For increasing, I want this order. A1 less than equals to A2, less than equals to A3. This is what I want for increasing. And for decreasing, I want this. And neither of this is happening here. This is not happening, and this is not happening either. What's happening is A1, this is less than, I can write less than equals to A2, then this is greater than equals to A3, then this is less than equals to A4. That means it's neither decreasing nor increasing. So the sequence that's given to you, this one, is neither decreasing nor increasing. This option is incorrect. And coming to the third one, 1 by n. So we'll do the same thing here. We have to check the sign of. If an minus an plus 1 is greater than 0, then is it increasing or decreasing? Well, let's take this one. If an plus 1 minus an is greater than 0, and the other cases when an minus an plus 1 is greater than equals to 0. Or maybe I should write this as an plus 1 minus an less than equals to 0. If this is true for all n, then it's increasing. If this is true for all n, then it is decreasing. Now, if for some n this is true and for some other n this is true, that means it's neither increasing nor decreasing. That's what happened in our last case. So this time our sequence is this one. An is equals to 1 by n. Let's find the sign of an. So whether it's increasing or decreasing is decided by the sign of an plus 1 minus an. So an plus 1 minus an gives me 1 by n plus 1 minus 1 by n, which is n minus n plus 1 by n plus 1 and n. Now we know that n plus 1 is positive, n is also positive. And what about this one? This expression is minus 1, right? If we'll simplify it, we'll get minus 1 here. I can simply write minus 1 in the numerator. This is the simplified version of this, right? So this is negative, all of them positive. That means this is negative. That means an plus 1 minus an is negative, which means your sequence is decreasing, right? So this implies 1 by n is a decreasing sequence. So this option is also incorrect. And coming to this one, D1. In the D1, you don't even need to use the definition. You can clearly see that each term is, although we'll do it by definition too, we'll do it both ways. This is summation 1 by k factorial, k varying from 0 to n. This is given to be an. That means your sequence is simply, if I'll put 0 here, I'll have 1. Then in next one, I'll have 1 plus 1. Then in the next one, I'll have 1 by 2 factorial. Not here. Here, the next term will be 1 plus 1 plus 1 by 2 factorial. Then the next term will be 1 plus 1 plus 1 by 2 factorial, 1 by 3 factorial, and so on, so on. Now what's happening here? This is your sequence. You have 1 here, then you added something positive, then added something positive, then added something positive. So each time you're adding something positive, which means your sequence should be increasing, right? Is this okay? Does anyone have a doubt in this approach? I'll need at least someone to respond.
No, ma'am.
No doubt, ma'am.
Okay. So this is one approach where you see, and when everything positive is involved, what happens is if this is happening, then it could be a problem. K factorial. What happens is if you will take this sequence, k varying from 0 to n, what will this sequence be? This is also a sequence, right? What kind of sequence is this? This is
Neither increasing nor decreasing.
okay. Let's see. This will be, you will have first term will be 1. Then the second one will be 1. and then you'll have 2 here, no, 1 here and 1 here. No, the first one will be minus 1 to the power 0. Yeah, so this will be 1, and the second one will be 1 plus minus 1 to the power 1 by 1 factorial. So it will be minus 1. So this term will be 0. Then the next one will be 0 and then plus minus 1 to the power 2 by 2 factorial. So this will be 1 by 2 factorial. This third term will be 1 by 2 factorial. Then next will be 1 by 2 factorial minus 1 by 3 factorial. Then this will be 1 by 2 factorial minus 1 by 3 factorial plus 1 by 4 factorial, right? And it will keep going on like this. Now about Bn, first you have 1, then it decreases to 0, then it increases to 1 by 2 factorial, then it decreases again because you've subtracted something, you've subtracted a positive number from 1 by 2 factorial. That means this is decreased, right? 1 by 2 factorial is less than 1 by 2 factorial minus 1 by 3 factorial, right? So this has decreased. From third term to fourth term, it has decreased. Then it has increased again because you've added 1 by 4 factorial. Then it will decrease again. That means this is neither decreasing nor increasing. So this sequence is but this one is an increasing sequence because each time you're adding something positive. This term and the next term is something positive added, then the next term is something positive added again. That's why this is an increasing sequence. Now instead, let's say if I'll take summation k varying from 0 to n, and I'll have minus 1 to the power, not minus 1 to the power, this time let's take minus 1 by k factorial. Now if I have this thing, then this will be minus 1. So this is the same as this one, but you have negative signs this time. So this will be minus 1, minus 1, minus 1. Then you will have minus 1, minus 1, minus 1 by 2 factorial. Then minus 1, minus 1, minus 1 by 2 factorial, minus 1 by 3 factorial. So what are we doing in this one? So you had minus 1 first, and then you subtracted 1 from this one. That means it has decreased. From here to here, you have this value has decreased. Then from here to here, it has decreased again, right? Because you subtracted another positive. This is a positive number, and you've subtracted it from this one. And then it has decreased again, and then it has decreased again. So it keeps decreasing. That means this is a decreasing sequence. And if you want to use the definition, you can use that too. You can do an plus 1 minus an and see whether it's greater than 0 or less than 0. So if you solve this, do we need to do it this way? This will be k varying from 0 to n plus 1 minus summation k varying from 0 to n. Now if I take, and these things are same, right? 1 by k factorial here and 1 by k factorial here. And if I have summation just 1 second. So if I have this thing, let's say I have summation Cn, n varying from 0 to, let's take Ck instead. If I have summation Ck, k varying from 0 to n plus 1, and I have summation Ck, k varying from 0 to n, that means this is C1 plus C2, C0 is also here, so on till Cn plus 1. And this other one is C0 plus C1 plus so on till Cn, right? So you'll only be left with this term, right? Everything else gets cancelled. So this is just Cn plus 1. The n plus 1th term remains and everything gets cancelled. So this one should be this one should be 1 by, if you're considering this as Ck and this as Ck as well, then the term that left was Ck plus 1, right? The term that got left was Ck plus 1, and Ck plus 1 here is 1 by n plus, sorry, not Ck plus 1, it was Cn plus 1, right? So this will be 1 by n plus 1 factorial. So this thing will be 1 by n plus 1 factorial, which is greater than 0, right? This is a positive number. This is n plus 1. Any factorial, 1 divided by any factorial, 10 factorial, this is always positive. So that means this is greater than equals to 0. That means an plus 1 is greater than equals to 0 minus an. This is greater than 0. I can write an greater than equals to an, which means it's increasing, right? So this is an increasing sequence. Using the definition, if you have to use the definition, we've also done it that way. Okay, so this is the next question. This one. This will be, how can we do this one? This is the same as when we said, when you have anything like this, x20, let's say we have x20, 25 plus 1 by x 2025 plus x 2024. If you have something like this, then you have to divide by highest power, right? So, especially when it's going to infinity. If you have this going to infinity, that means if you'll have this in the denominator, this will go to infinity, this entire thing will go to 0. So that means you have to divide this entire numerator and denominator by the highest power, x to the power, the highest one. So the highest one is x to the power 2021. So you have to divide both these things by x to the power 2021. So you will get x to the power 2021 by x to the power 2021 plus x to the power 2020 by x to the power 2021 and x by x to the power 2021 plus 1 by x to the power 2021. Similarly, here in the denominator, you will have x to the power 2021 plus 2021 x to the power 2020 by x to the power 2021. And here you have 2021 divided by x to the power 2021. So let's see this, what happens to the numerator first. So this entire thing in the numerator, we have to take x tending to infinity. This will be 1. This will be 1 by x. Then the next is 1 by x square, right? Because these are decreasing. You have x to the power 2021, then x to the power 2020, then x to the power 2019. Then you will have 1 by x cube and so on, so on. And here you will have this one, which is 1 by x to the power 2020 and 1 by x to the power 2021. This is your numerator. And the denominator will be 1 if you will divide this thing by x to the power 2021. This thing will be 2021 by x. Then the next will be 2021. If they're following this pattern, I think, yeah, they've multiplied everything with 2021, right? So this will be 2021 by x square. Then the next one will be 2021 by x cube plus so on, so on. And here towards the end, we have 2021 divided by x to the power 2021. We have just cancelled these ones. And this is the form that we have gotten. So now if x tends to infinity here, this is 1, this will remain 1. This term will go to 0. This term will go to 0. This term will go to 0. Similarly, all of these will go to 0. So you will have 1 plus 0. And there also, this term will go to 1, the first term. This will go to 0. This will go to 0. And similarly, all of these will go to 0 because you have x cube, x powers in the denominator, and there's just a constant in the numerator. So you will have 1 as answer. Is this fine? Can we move to the next question?
Yes, ma'am.
Okay.
Madam, why the
Yes.
denominator goes to 0? Means,
These ones, if you have, let's say you have a constant k divided by x to the power n, then if x tends to infinity, where does this go? This is just a constant. That means in the numerator, you have something fixed, and in the denominator, you have something tending to infinity. That means you have 1 by infinity form, right?
it tends to 0. Achha, okay.
Okay. So even if you can see that you don't have to have constant in the numerator in particular, even if you have something like this, let's say if you have an by bn, where an is bounded. What do we, I'll just write what we mean by bounded. Have we discussed bounded sequences? This is definition. A bounded sequence an is, so we say an is a bounded sequence if an is, or I can say mod of an is less than some constant, where this constant is a real number. So if every term is less, the mod of every term is less than k, or equivalently you can say if an lies between two constant numbers, let's say k and k dash, where k and k dash are real numbers. So if an lies between k and k dash, let's say there's a sequence an and it lies between 2 and 3. That means it's a bounded sequence, right? Because it's bounded below by 2, it cannot take value less than 2, and it cannot take value greater than 3. That means it's bounded, right? So that's the meaning of a bounded sequence, where each term is, all your terms are greater than equals to some number and they're less than equal to some number. Some fixed number. These numbers have to be fixed. Right? That's your bounded sequence. So you can take this example. You can take 1 by n, for example. If you take 1 by n, your 1 n is less than equals to 1. So it's bounded above by 1 and it's bounded below by 0, right? That means it's bounded. Okay. Now, if I have an bounded and bn is, let's say bn tends to infinity, then what will be the limit of this one? An is bounded and bn is tending to infinity. That means this can take bounded values only, but this can go to infinity. This can keep increasing, but this can take only bounded values. What should this go to then? This will go to 0. So if you have a bounded sequence in the numerator and an unbounded sequence which is tending to infinity, in the denominator, that means the limit of this entire quotient will be 0.
Then say just keep decreasing.
Yeah, it will keep, you see this, right? If an is bounded, that
If-
means an, let's say an is bounded by k and k dash. Then an by bn will be bounded by, it's tending to infinity. That means eventually it's greater than 0, right? When a sequence tends to infinity, what does that mean? That means it keeps growing, right? It keeps increasing. That means eventually, towards the end, after a certain stage, after certain, let's say after B30, it will be greater than 0. If it will remain less than 0, then how can it tend to infinity? Right? Infinity is on the positive side. That means Bn is positive eventually. So I can divide by Bn on all sides here. So I'll have k by Bn, and this will be k dash by Bn. And this is, now you have to use the sandwich principle, where we say that if a sequence, this is one sequence, these are two different sequences, and this sequence always lies between these two sequences. That means limit of this sequence. What is the limit of this one? The limit of this one is 0. And the limit of this one is also 0, right? Because Bn is tending to infinity and this is just a constant. So that means your limit an by Bn is also 0 by sandwich principle. This is the proof of this thing.
How the first one is become 0 by that means k by b of n. This would be 0.
This is not 0. The limit of this is 0.
Acha.
Limit of this, limit, and limit. We have taken limit on all three of them. Okay. So what were we discussing? This one, right? Okay. So let's discuss this question then. Just 1 second. So let's come to this one. This is the next question. This is A and Bn are given to be two sequences, and we are talking about, we're done with the last one. Okay, we're not done with this one either. Let's do this one first. So, and this is about boundedness. A sequence, we have discussed what a bounded sequence is. We say that An is a bounded sequence if it is bound. Should I write the entire thing here? Bounded above and below and all of it? Because I don't think we've discussed it in lectures. So I'll write it here. Before coming to this question, I'll write what bounded below means. So we say a sequence is bounded below. An is bounded below. This means that An is greater than equals to some constant number for all n belonging to natural numbers. That means A1 is greater than equals to k, A2 is also greater than equals to k, and so on till An is also greater than equals to k for all n, right? And k is a constant. You can't keep changing this one. K is a constant which belongs to real numbers. Then we say that it is bounded below because it is bounded from the lesser side, right? That means your An is always greater than equals to k. So it's bounded from here. Your An is always on this side, on the real line, right? That's why we say it's bounded below. Then the next one is bounded above. So bounded above means we say An is bounded above or Bn. if Bn is less than equals to some constant k for all n belonging to natural numbers, and k is a constant belonging to real numbers. And then comes bounded sequence. So we say Cn is a bounded sequence if Cn is both bounded below and bounded above. And above. That means I want it to be bounded below. So Cn should be greater than equals to some k, and Cn should be greater than equal to some k dash. They don't have to be same numbers. That's fine. But I need numbers such that Cn is always greater than that number, and another number, it could this number where Cn is always less than k dash. For all n belonging to natural numbers, and k dash are fixed constants belonging to real numbers. Now let's come to the question. The question is, and the definition of monotonically increasing and decreasing, which we already have discussed, is given to you here. So which of the following statements regarding the convergence of a sequence is correct? Let's say there's a monotonically increasing sequence, and we say that it is convergent. So let's take this first one. Option A says that if an is monotonically increasing, this is given to me, then an is convergent if and only if it is bounded. We have to see if this is true or not. So let's say I have a sequence an, a1, a2, a3, and it is increasing. That means a1 is less than equals to a2, a2 is less than equals to a3, and this trend keeps going on, right? This is a given sequence, and I have to show that or disprove that an is convergent. Let's take an to be convergent. If I say that this is convergent, let's say this is going to a. What does it mean? Let's say we have an increasing sequence, and if it keeps increasing without a bound, keeps increasing without a bound means like this one, 1, 2, 5, or let's take 1, 2, 1, 3, 5, 7, 9, 11. Now this is a sequence, it's an increasing sequence, and it keeps increasing without a bound, right? There's no bound to it. It'll keep increasing. Can I say that it is convergent? This is a divergent sequence, right? It's increasing and it's divergent. What does it mean? That if I'll take a sequence which is increasing without a bound, that means it's divergent. So increasing plus no bound, this implies divergent. Or in simple words, you can say if an is increasing and it has no bound, that means an will tend to infinity, right? So if it's given to you that an is increasing and I want it to be convergent, then what should I take? I should take it to be bounded, right? Because if I'll take it to be unbounded, I know it's divergent. So if I want this to be convergent, I'll have to take it to be bounded. Is that okay?
Yes, ma'am.
So that means if you'll take an increasing sequence and if it's given to be a convergent sequence, then it has to be bounded. Similarly, let's say you have been given that there's an increasing sequence and it is bounded. That means there's a sequence A1, then A2, then A3, keeps going on, but there's always a bound. That means all of these terms, this is greater than this is greater than this, they keep increasing, but all of them are less than some number. This is less than some number, k. All of them. That means they have to converge to some number, right? Because they cannot move to infinity. So we're not getting into the literal proof of it. But if you have a bounded sequence, then this implies that it will be convergent. So if a sequence is given, and same happens for decreasing ones too. That means if you have God, just 1 second. That means if we have, and this holds for decreasing sequences too. Now, what do these things give us? This gives us this entire thing gives us that if an is an increasing sequence, then an is bounded if and only if it is convergent. So an increasing sequence is bounded if and only if it is convergent. Or you can say an increasing sequence is convergent if and only if it is bounded. Same happens, this conclusion we have drawn from here. Convergent, if this is an increasing sequence, and convergent implies bounded, and bounded implies convergent. So for increasing sequence, convergent and boundedness imply each other. Now the same holds for decreasing sequences too. Similarly, if an is a decreasing sequence, an is bounded if and only if it is convergent. That means increasing sequences, or we also call them monotonic sequences. So monotonic sequences are convergent if and only if they're bounded. This is true for monotone sequences. Is this okay? Is this clear to everyone? Because the options are based on these details only. So monotonically increasing sequence is convergent if and only if it is bounded. We have just done this. This is true. All monotonic functions are convergent. So if you have a monotonic function, we have just seen it. If I have a function and it is monotonic, that means that function is either increasing or that function is decreasing, right? No matter whether it's a function or it's a sequence, the same applies to both of them. If your fx is an increasing function, I'm only talking about the function for now, but the same holds for sequences as well. If your function is an increasing function or it's a decreasing function, then we have just seen, in case of sequences, we have seen that f is convergent if and only if it is bounded, right? That means if it is convergent, then it has to be bounded. And if it is bounded, then it has to be convergent. And this one says all monotonic functions are convergent. What do you think about this one? Do we have any doubt in what we've discussed here?
I have a doubt.
Yeah,
If we only have a lower bound,
yeah.
then will that be considered as a convergent function or not? Because it still doesn't end anywhere, but it has a starting point.
Okay, let's say you have 1 by n, right? Or let's not take 1 by n, let's take n plus 1 by n. Can I take this one? Now n plus 1 by n is, it's always greater than 0, right?
Okay.
This is a natural number. This is also positive, so this is always greater than 0, but it has no upper bound, right? Because you have n here and it keeps increasing. So that means you don't have an upper bound here, but it's bounded below. Now, do you think this can converge? This will be
No.
1 plus 1. Then you'll have 2 plus 1 by 2. Then you'll have 3 plus 1 by 3. That means each time it keeps increasing and without a bound. No bound. no upper bound. That means it can't converge, right? So when you say that there is, and the problem here is that it's an increasing sequence, and we know that increasing sequence are only convergent when they are bounded, and bounded means both bounded below and bounded above, right? And if you want to really simplify this one, no, I don't want to confuse you guys, but if you have been given an increasing sequence, then instead of this, if it's an if a sequence is increasing, then isn't it obvious that it's bounded below? Because if this goes on, a1 is less than equals to a2 less than equals to a3, then can't I say that a1 is the lower bound of this sequence, because all the terms are greater than a1, right? So every increasing sequence is automatically bounded below. So you only are left to check whether it's bounded above or not, right? So if you have an increasing sequence, then instead of saying that it is convergent if and only if, this is also true. Convergent if and only if bounded, this is also true. But because we know that increasing sequences are always bounded below, so I can simply say convergent if and only if bounded above, right? You can just check this thing and it will be fine. Yeah.
Bounded above means bounded.
Bounded above means if you have a1, a2, a3, if this is a sequence, then I say that this is bounded above if each term of this sequence is less than equals to some constant. Then I say it's bounded above. We have an upper bound, right? There's a number that bounds them from above, from here. It bounds them from above because they're all less than this, right? They're all smaller than this. That's why it's an upper bound.
Means this is decreasing.
You asked the meaning of bounded above, right? We just discussed what's the meaning of bounded above.
No,
What's
no.
your question?
You said that ki bounded. You mentioned that what you mentioned that this arrow bounded above. That's what I need
Okay.
to understand.
If you have an increasing sequence, you have an increasing sequence, right? Increasing an. That means a1 is less than equals to a2 is less than equals to a3, and so on, right?
Correct.
Now, isn't this bounded below? Because a1 is, for bounded below, what do you need? You need a number such that each term is greater than that number, right? You want k such that all the terms are greater than k, right? So can't I take a1? All terms are greater than a1, right? a2 is greater than a1, a3 is greater than a2. That means a3 is also greater than a1. Same goes for a4, then a5, then a6, right? That means you have a lower bound. So if you have an increasing sequence, it is obvious that it's bounded below. Similarly, if you have a decreasing sequence, it's obvious that it's bounded above, right?
That's what I'm asking. For a decreasing sequence, there is one above upper bound.
Yeah. An is bounded below. And if this is decreasing, then an is bounded above. So if you have a decreasing sequence, instead of saying that convergent, this is convergent if and only if it is bounded, I can say convergent if and only if it is bounded below, right? Because it is automatically bounded above. So you don't have to check whether it's bounded above or not. That's obvious because it's a decreasing sequence. So it's inherent. Now you only need to check whether it's bounded below or not, right? Is this okay? So here you have, now this option says all monotonic functions are convergent. Now let's say you have a monotonically increasing function. And can I say all monotonically increasing functions are convergent? Functions and sequences work in the same manner. So if they're saying that f is, let's say f is monotonically increasing, what's the option? And can I say it's convergent? With just this information, can I say that this is convergent? This should be convergent. Let's take this one. 1 is mapped to 1, then 2 is mapped to 2, 3 is mapped to 3. That means this has 1, 2, 3, 4, 5. This is definitely increasing. Can I say it's convergent? And we just saw that if an increasing function has to be convergent, then it needs to be bounded. That means all increasing functions cannot be convergent. Only bounded increasing functions can be convergent, right? That means this should be incorrect. If you want a counter example, the counter example was this. F from natural numbers to natural numbers, where Fn is, you can take it to be 2n. That's also fine. This is an increasing function, but it is not convergent. And first thing is, whenever this option is actually terminologically speaking, this is slightly inappropriate to write in this manner, because we don't talk about convergence when we talk about functions. So convergence is only for sequences. We don't talk about convergence when we're dealing with functions. But okay, if you'll take sequences here, you can take sequence here. So this is incorrect, and we have seen a counter example, right? Can we move to the next option? Is the B part clear? So the C part is a monotonically decreasing sequence is convergent if and only if it is bounded below. And we've seen it here, right? We saw this here. Where is it? Where did we write that thing? The bounded, this bounded below, bounded above stuff here. So we've written it here. So a decreasing sequence is convergent. We have seen it here if and only if it is bounded below, right? So that means this option should be correct. A monotonically decreasing sequence is already bounded above because it is decreasing. That's why it's bounded above. So it's convergent if and only if it is bounded. That means if and only if it is bounded below, right? That means this is correct. If anyone has a doubt in any option, you can unmute yourself and ask. Then the last one is a monotonic sequence is convergent if and only if it is bounded. So a monotonic sequence is a sequence that is decreasing or a sequence that is increasing. So those kind of sequences are called monotonic sequences. That means this is the collection of increasing sequences or decreasing sequences. This is this collection. And they are convergent if and only if they're bounded. We have seen this, that a decreasing sequence is convergent if and only if it is bounded, and an increasing sequence is convergent if and only if it is bounded. That means a monotonic sequence, which is the collection of increasing sequences and decreasing sequences, is convergent if and only if it is bounded. That means this is correct. Can we move to the next question if this one is clear?
Yes, ma'am.
Yes, ma'am.
Yeah.
Okay. So just 1 second. This is the next question that we have. So this is, you have been given two sequences, and you have to determine the conditions which will ensure that. So it's like this. If this condition is, you have to determine the condition such that this condition ensures that AN and BN is convergent. So I want a surety that if this condition holds, then your A and BN should be convergent. You have to determine those conditions. Let's see. If AN is convergent, can I say AN and BN both are convergent? A and Bn, the product is convergent. For the first one, let's take an to be 1 by n, and let's take bn to be n square. Now 1 by, this is convergent, right? This is divergent. But they said if an is convergent, then an bn is n divergent. That means the convergence of an is not enough to ensure that an bn is also convergent, right? Same happens with the second one. So an is convergent and bn is divergent. This is you can use the same example for this one. For a and b, you can use the same example. You have taken an to be convergent, bn to be divergent, and we have seen an example where when an is convergent, bn is divergent, a and bn is divergent. And this option says that if an is convergent, let's do b here. So if an is convergent, this is convergent, and bn is divergent. Can I say from this information that an and bn is going to be divergent? We have seen an example where a and bn was divergent, but can I guarantee that a and bn is going to diverge? Okay, you guys try to find an example for this one, and I'll be back in a minute. Could anyone find some example of this? Either you'll have to prove this thing, or you'll have to come with a logic why, whether when an is convergent, bn is divergent. This should imply, this is your question, right? Is this always true? Then either you need to find a counter example where an is convergent, bn is divergent, and a and bn is not divergent. That's one. And second is, or you have to prove that if an is convergent, bn is divergent, then a and bn should be divergent. So because it's a simple count, you can find a simple counter example. You have to take this convergent, right? Can you see? This is the hint. Try to look at this one, and with this one, try to find examples for this one.
So here, when you multiply, you get the n. So n cannot be convergence. N is increasing. So
There is no concept of increasing, decreasing in this one. We have just been given two sequences, an and bn, and you have to, the first option says that if an is convergent, can I say an and bn is convergent? Then we have found a counter example for this where an was convergent, but bn, and this is bn, then a and bn is not coming out to be convergent. That means an being convergent is not enough to prove that an bn is also convergent, right? This was first option. Then second option says that if an is convergent and bn is divergent, can I for sure say that a and bn has to be divergent? That is the question. And the answer is no. I just want you guys to find out an example of an and bn where an is convergent, bn is divergent, and a and bn is also not divergent. That means an example where an is convergent, bn is divergent, and a and bn is convergent. You have to find one such example, and this is your hint. Take the hint from here. You just
This
have to think a little.
always, depending upon
Yeah.
the value of the AN and BN.
Okay. Let's take, we said that you have to take a hint from here. If I'll take A and to B, because this has to be convergent, right? So let's take A and to be 1 by n square instead. The problem is if I'll take it to be 1 by n, then this is convergent. And if I'll take it to be n square, this is divergent. This is fine. But what comes out is n, which is divergent. So this will support this statement, right? If I'll take an to be 1 by n, bn to be n square, this example is going to support what is written here. And I am trying to find a counter example. So what I've done is here is instead of an square, because we know when we do a and bn, this diverges means this goes to infinity, right? So I want the power, I want the one that is the converging one to dominate. I want the converging one to dominate means if this is 1 by n square, if I take this 1 by n square and if I take bn to be n, then this is going to dominate because it has two power. This has just one power, right? So if you do a and bn, you will have n by n square, which is 1 by n. Now where does this go when n goes to infinity? This goes to 0, right? That means this converges. So this is an example where an is convergent, bn is divergent, but the product is convergent.
Yeah. So depending upon the value, it will be na
Depending upon the value of what?
AN and BN.
This is a general statement. What happens is when you've been given a general, I don't quite understand what your question is, but if it is this, then if you've been given, what's given is an is convergent and bn is given to be a divergent sequence.
Means it is not true always.
Yeah, it's not true always. So if it's true always and that's not given to you, you have to decide whether it's always true or not true. So if it's not true, you need to find a counter example, which we have done for not true. And if it is true, then you need to prove it. That means you'll have to do something to show that this is always true. If an is convergent, bn is divergent, then the product has to be divergent. Then prove it. Is this okay?
Yeah.
So we have found a counter example. Then the next one is an converges to 0 and bn is divergent. The C part is if an tends to 0 and bn is divergent, then can I say that a and bn is convergent? Okay, so for the, I think this first option is incorrect, right? Because we have seen a counter example for this one. But for this one, an is convergent and bn is divergent. We had to see if what have we seen here? This was not the right counter example, this one, because this is the counter example for this one, that if an is convergent, bn is divergent, then a and bn is not divergent always, right? It can be convergent and it can be divergent too. If an is convergent, and for that the example is this one, an is convergent, bn is divergent, product is divergent. Here we had an is convergent, bn is divergent, but the product is convergent. That means if one is convergent, the other one is divergent, we can't really say about the product, right?
Yeah.
So that means, and this one says that if an is convergent and bn is divergent, can I confirm that a and bn is convergent? So I can't confirm it, and I can't confirm that it's divergent either. I can't confirm that the product is convergent and can't confirm that it's divergent either. It can be convergent, can be divergent depending on your sequences that you've chosen. Then coming to the third one, an is convergent to 0 and bn is divergent. Now if I say an tends to 0 and bn is divergent, then can I say that the product is, what can I say about the product? Can I say something about it? What's happening here is if you have A and Bn, An is going to 0, this is going to infinity. It's divergent, that means it's going to infinity, right?
Yeah.
Either it's going to infinity, and the other cases, this is generally considered to be an oscillating case. Such cases are considered to be oscillating, but in our syllabus, I guess we count this under divergent, right? This also we consider as divergent. So if I have An tending to 0, this form is, if it's actually tending to, if Bn is divergent, then let's take, this is counter example. Let An be a sequence that goes to 0. You can find a lot of sequences of that kind, and Bn be a sequence that goes to infinity. For example, let's take the same one. Bn is converging, Bn is n square and An is 1 by n. Then An, Bn we saw was n, and this is divergent, right? That means if An is convergent, Bn, or we wanted this to go to 0, this does go to 0, right? An goes to 0. So if An goes to 0 and Bn is divergent, then A and Bn can be divergent, right? Then there's one more example. So can I say that this is always going to be divergent? If An is going to 0, Bn is divergent, and can I say that it's always divergent? And that's not true either, right? We have seen this one, the previous example where we took 1 by n square, and n was an example where this is going to 0, this is divergent, but the product is converging. That means in this example, in this case too, you can't predict. If An is going to 0, Bn is divergent, you can't predict about the convergence or divergence of A and Bn. Can't predict convergence of A and Bn in this case. And in the previous one also, we can't predict, right? And by the way, in this one also, the first one also, we can't predict. We can't for sure say that if An is convergent and there's nothing given about Bn, then A and Bn is going to be divergent. We can't tell whether it's divergent or convergent. So this is also incorrect. And then coming to this one, An and Bn. Now, if both are convergent, let's say you have D, where An is converging to A and Bn is converging to B. That's what we've studied in the definition of convergence, right? That these numbers have to be finite. Then A and Bn, and we have seen this in the previous lecture, that if An goes to A, Bn goes to B, then A and Bn goes to AB. That means A and Bn is also convergent. That means this option is correct. Okay, so this is the next question. You will have to use the identities that we have discussed in the class yesterday. So this expression simplifies to sine square theta plus cos square theta plus 2 sine theta cos theta. And this one is 2 times 1 plus sine 2 theta. Now there are two things here. One is this identity, and the other one is this one. So sine square theta plus cos square theta is equals to 1, and 2 sine theta cos theta is equals to sine 2 theta. So this entire expression simply gets simplified to 1 plus sine 2 theta divided by 2, 1 plus sine 2 theta. This will just be 1 by 2. This is the simplification of this one. Then this is the next example. You have to find the limit of An. So the best way, first thing is we see something common here. This is 12. and this is 3 and 27. So we can take 3 common and simplify the expression to 4n square by n plus 9 minus 4n square plus 23 by n plus 5. And for this one, if I'll directly use this, if I'll simplify them separately, you will have n square, and n is tending to infinity, right? So you will have, if I'll divide this by n square, I'll have 4 by 1 plus 9 by n. So instead of solving this entire thing, I think it's easier for you to do them separately. This is 4 by 1 by n plus 9 by n square. So we've divided numerator and denominator both by n square. Then in this one, we'll do the same. So this will be 4 plus 23 by n square. And here you will have 1 by n plus 5 by n square. Now if n tends to infinity, this is equals to, this goes to 0, this goes to 0, and this is just 4. So you're just left with 4. And here you're left with, this goes to 0, this goes to 0, and this expression also goes to 0. So you're left with 4. So this is 0. And I think just 1 second. Okay, so
So here there comes the 4 by infinity minus 4 by infinity. This kind of things comes. N tends to
okay,
infinity.
this is just 1 second. This is when n tends to okay. That's fine. I thought this is the denominator is coming out to be 1 just, but that's not happening, right? This is going to 0. So the denominator in both the cases is going to 0. That
Correct.
means this will be infinity. Okay, did we miss this form? This is also an indeterminate. One of these, this is also one of the indeterminate forms. This is also one of the indeterminate forms. And what happens when you have indeterminate forms? That means you need to find some other way. You can't find the limit from here. So this approach has failed. So we'll have to switch to some other approach. That means we'll have to simplify this thing. So let's simplify this expression. What will we have here? 4n square, n plus 5 minus n plus 9. And this is 4n square plus 23. And this is n plus 9, n plus 5. So the simplification of this will be 4n cube plus 20n square minus 4n cube minus 23n, 36n square minus 127, right? And if I'll simplify this entire thing, I'm not solving this one for now. I don't want unnecessary calculations. Let's see if we can do this without simplifying the denominator. So this will give us, these to get cancelled, then this will be minus 16n square, right? Then minus 23n and minus 127. Minus 23n. Is it 127 though? No, right? It's something else, but it doesn't matter. It's some constant. Not multiplying this thing, it's some constant here, and you'll have some constant here. So this is this, and you have n plus 9 here and n plus 5 here, and you have to find the limit of this when n tends to infinity. Now both of them have 2 and 2 here, so you can divide both of them by n square, right? If I'll divide the numerator and denominator both by n square, what will I get? I'll have minus 16 minus 23 by n minus k by n square. And why this k does not matter, the constant does not matter, because this term, when n tends to infinity, this term will go to 0. That's why it does not matter. Here you will have, I have to divide the denominator by n square, so I'll divide this by n and this by n. So I'll get 1 plus 9 by n, and here I'll get 1 plus 5 by n. So this is when n tends to infinity. Where does this expression go? This is minus 16. This will go to 0. This will go to 0. This will go to 0. And this will also go to 0. That means you're only left with minus 16 in the numerator and 1 multiplied with 1 in the denominator. That means it's minus 16.
Yeah.
So that should be the answer. Is this fine?
Means in this case, you need to solve it, simplify it.
Yeah, you will have to simplify it, because we've seen that if we try to do it this way, you will get infinity minus infinity form. And that's an indeterminate form. So you'll have to simplify it. And when you simplify stuff, no, it's not necessary that in this particular case, your infinity by infinity, this was an indeterminate form. But when you simplify things, simplify this form, it sometimes gets converted into infinity by infinity form or 0 by 0 form. But it's still a better form, because we can use L'Hopital's rule here, right? 0 by 0 form, you can use L'Hopital. Here you can use L'Hopital, but in this form, you can't actually use L'Hopital's rule, right? L'Hopital's rule is for f by g, where this is 0 by 0 form or infinity by infinity form. This is what L'Hopital's rule is for. You can't use it for f minus g kind of functions where both are going to infinity. Here, it's not applicable, right? So in our case, infinity minus infinity form got simplified to a form whose limit you can determine, but sometimes it also gets converted into another indeterminate form of some other kind, 0 by 0 or something. Okay. So we have, I think, a few more questions. One question here and
Ma'am,
one
one
here.
question.
Yeah.
Supposedly, if we had infinity plus infinity, so could
Yeah.
we just interpret that to be infinity, or yet we can't solve it further in that?
Okay. That's infinity only. Infinity plus infinity. Infinity is actually a number that's very large. It's not even a
Yeah.
number. Infinity is usually a limit, right? So if you add infinity to infinity, that means you're growing. This means increasing. It keeps growing without a bound, keeps growing without a bound. So the sum will keep growing without a bound. That's not a problem, right? But if I say an minus bn, this keeps growing without a bound, keeps growing without a bound. But I can't say this the same about this one, right? It might be something finite, it might be bounded, we don't know. So that's why infinity minus infinity is something that you can't predict, but infinity plus infinity, I'll write it here. Infinity plus infinity limits, this is for limits. When you have an plus bn and the limit of both of these is infinity, then I can just say that the limit of sum is also infinity. So if you have infinity and infinity limits, then the overall limit is also infinity. When you have infinity minus infinity, this is one of your indeterminate forms. You can't determine this. You will need to use either L'Hopital's rule, convert it to some other form, convert it to 0 by 0 form or infinity by infinity form, and then solve it. Then you have 0 into infinity form, or let's do infinity into infinity form. This is also infinity. But if you have 0 into infinity form, this is a problem. Indeterminate form. If you have 0 by 0 form, that's also indeterminate. If you have 0 by infinity form, this is just 0. If you have infinity by 0 form, this is just infinity. If you have infinity by infinity form, that's an indeterminate form. If you have 0 to the power 0 form, let's say that when I write these things, I mean an to the power an sequence and bn sequence, where an is going to 0, bn is also going to 0. That's what I mean, right? But in simple words, I'm just writing it this. This is also one of the indeterminate forms. You won't be getting these forms. Don't worry about this. Indeterminate forms. And then you have infinity to the power infinity. This is also one of the indeterminate forms. 0 to the power infinity. This is also indeterminate form. These are all indeterminates. Is this okay? Or let's just forget these two. Let's just see, because this is what you're likely to have in your syllabus. This is an indeterminate form. And usually these kinds of form, let's say you have an to the power bn, where an is going to 0, bn is going to infinity, is convertible to an infinity by infinity or 0 by 0 form. How do we do that? You can just simply use log here. So let's say this is going to some c, then log of an bn goes to log of c, right? And then this will be bn log an going to log c. So this will mean log an. Now, if an is going to, we add an going to 0. If an is going to 0, that means your log of an is going to minus infinity, right? I can write this as bn into log of an as log of an by 1 by bn, right? This goes to log c. Now, what is this? This goes to minus infinity. If an goes to 0, log an goes to minus infinity. And if bn goes to infinity, 1 by bn goes to 0, is it? We had bn going to infinity. Wait a minute. This is going to 0, this is going to infinity. Bn here, log an here. Okay, if your an goes to an is going to 0, right? If an goes to 0, log of an goes to minus infinity. And if bn goes to infinity, this thing goes to 0. This will just be infinity form then, but it should be indeterminate. Just 1 second. Let's not get into this one. I'll have to check this one. There's a way to convert it into the 0 to infinity power. We have a way to convert it to 0 by 0 form and 0 infinity by infinity form. We'll do it. Do we have a question of that form? No. Do we have a question of that form in assignments? 0 to where you get 0 to the power infinity form. I think we have one. I'll have to check this. Just 1 second. Okay, I don't think this is not an 1 to the power infinity, I guess, is an indeterminate form. Yeah, 1 to the power infinity is an indeterminate form. That way it works. If you have an going to 1 and bn going to infinity, then this is an indeterminate form. Now, if I'll do the same things here, I'll have an to the power bn going to c. This will be log an bn going to log c. Your bn is going to, then you can write this as log an by 1 by bn. So bn is going to infinity. This thing goes to 0. This entire thing goes to 0. And an is going to 1. So this entire thing goes to 0. Then it becomes 0 by 0 form, right? So this is where you convert 1 to the power infinity form to 0 by 0 form.
But 1 to the power infinity is 1. Na?
No, it's indeterminate. We just saw it, right? It's indeterminate form. 1 to the power infinity is indeterminate form.
1 to the power anything is 1. Even if-
Anything is 1, but to the power, if you keep increasing the power, this is not 1. First is this is a sequence that's converging to 1. When we write, okay,
Okay,
when we
okay.
write 1 to the power infinity, infinity is not a number, right? So when we write 1 to the power infinity, as I discussed, this means this is a shorthand for an to the power bn, where bn is converging to infinity and an is converging to 1. So we don't have 1 here, we have a sequence that is converging to 1. We don't have infinity here, we have a sequence that's converging to infinity. Similarly here, you don't have infinity by infinity. That's not even a number. That's nothing. This is a form, which means there's a sequence an by bn where an is going to infinity, bn is also going to infinity. That's when we say it's indeterminate form. Is that okay?
Then we take the log and make it a 0 by 0.
In this one, you don't take log. Don't take log here. Don't take log. When in 0 by 0 form, infinity by infinity form, you can directly use L'Hopital's rule. Remember,
Okay.
we discussed L'Hopital's rule. So here you can use L'Hopital's rule. But when you have 1 to the power infinity, you can't use L'Hopital's rule here. So for that, you convert it to 0 by 0 form in this manner. And then you use the L'Hopital's rule. Is that okay? Now this will be in 0 by 0 form, converted to this one, and then use L'Hopital's. And for the other ones, we have other indeterminates too, right? 0 into infinity, this form, let's say you have an bn, where an is going to 0, bn is going to infinity. So I can write this as an 1 by bn, right? Where this is going to 0, this is going to infinity. That means this is going to 0, and 1 by bn is going to 0, right? So this I can write as, this form can be written as 0 by 0 form. And then you can use L'Hopital's rule. Similarly, this form can be written as 0 by 0 form or infinity. Why have I written? Okay, this is just 0, right? Where's the other, this kind of form? 0 into infinity. Okay, that's it. So when you have indeterminate forms, you're supposed to convert them to 0 by 0 or infinity by infinity form for you to be able to apply L'Hopital's rule, which you will do in next week. If you're familiar with derivatives, you must have understood it. But if you have not understood it, then you will need to do derivatives first. So there are 2 more questions left. Should we do those questions here, or maybe you can try these questions yourself? Because okay, we'll do them here only. Although we have done this in last class, we have done a limit like this in last class. Remember, this is the direct limit that we have done in important limits in the last class, where we said that 1 plus k by n to the power n okay, we didn't have product there, right? We just had this thing. We did this and we said n tending to infinity. What was this? We discussed this limit in the last class, right?
E power k.
e to the power k. So, and we have product here. That means we have 1 plus 1 by n to the power n plus 1 plus 2 by n to the power n. And this is still 1 plus 5 by n to the power n. So this converges to e to the power 1. This converges to e to the power 2. We have product here, right? We have product here, so this will be multiplied with each other. This is e to the power 1 and this is e to the power 5. So you have to do this. The result then will be e to the power 1, e to the power 2, which is e to the power 12, 13, 14, 15. So this should be correct. And this one, you guys can take the screenshot of this example and try this at home. You
Okay,
have to
ma'am.
use the identities that we've done in last class. You have to use those identities and what's given in the question. That's it. Okay. So can we end this class here? Does anyone have anything to ask?
Thank you.
Okay. So,
Thank you, ma'am.
okay. So we'll end this session here. Good night.